Okay, let's go ahead and get started. Hello, everyone, and welcome to today's presentation, Knowledge Graphs versus Property Graphs, a brief overview and comparison. I'll start by introducing you to our speakers. Today, we have Irene Polikoff. Irene is the CEO and co-founder at TopQuadrant. We also have Robert Coyne, and Robert is the Chief Marketing Officer and co-founder at TopQuadrant. Before we get started, let's review a few logistical items. Please feel free to ask questions as we go along by using your GoToWebinar controls. To post questions, please look on the right-hand side control panel. You should see a drop-down box for questions. If you click on the box, you should be able to post your question at any time during the presentation. We will address as many of those questions as we can at the conclusion of the webinar. We will also be recording the webinar and we'll send a link to the recorded version. And we will also present a brief poll. So thank you in advance for your participation. And with that, I will hand it over to Robert to get us started. Robert?
Thanks, Christy, and welcome everyone. Thanks for joining us. The topic of today's webinar seems to be of keen interest to a lot of people. A little background on TopQuadrant. We were founded in 2001. That was the same year that the vision of the semantic web was born. And since our founding, we've been applying this technology to create enterprise applications to make enterprise information meaningful. The technology has been variously known as semantic technology, semantic web, and linked data. But more recently, it's been widely known as knowledge graph technology, which is the topic of today's webinar. Since 2015, our focus is to provide comprehensive data governance solutions based on knowledge graphs. Today's presenter is Irene Polikoff, CEO of TopQuadrant. Irene has a long career in information management, and she has deep expertise in applying knowledge graphs to enterprise data governance challenges. In fact, she and other TopQuadrant personnel have been instrumental in helping to create and shape the standards for knowledge graphs through the W3C. In today's program, she'll first do a concise overview of these two main graph models, property graphs and knowledge graphs, using graph diagrams of the same example content to illustrate some critical similarities and differences. Then she'll dig a little deeper into the difference in meaning of some key terms used in both of these graph models and show critical differences in the capabilities that they each provide. Throughout the presentation, she'll cover and cumulatively list comparison points regarding the strengths and limitations of each approach. During the presentation, we'll take time for a quick poll, as Christy said, and Irene at times will dive into short demos using our knowledge graph-based environment, TopBraid Enterprise Data Governance, or TopBraid Edge, to show some examples of knowledge graphs and how they support capabilities for metadata management, governance, etc. And finally, she'll conclude with noting how knowledge graphs support data-centric systems and architectures by offering robust capabilities that support flexibility, evolvability, and other key kinds of capabilities. And she'll outline some steps to take if you're using property graphs and you want to convert them to knowledge graphs. So with that, I'll turn it over to Irene.
Thank you, Robert. And let me show my screen. All right, I'm going to start with some definitions of knowledge graphs, of a knowledge graph, because there are multiple. I mean, here is one, and here's another one. For each, you see some sources. There is yet another one from Wikipedia. So they have all phrased a little bit differently, but there are some common themes and elements in all of them. Namely that we are talking about data or real-world entities, as you see here, as well as the model describing them, and that's organized in a graph. And the first one talks about classes and relations in a schema. The second one talks about ontology, which is all the same as schema or a model. And the third one talks about the fact that there is knowledge as well as data, and we store semantics as well as real-world objects and information about them. So this is kind of a commonality of different definitions. We at TopQuadrant also have a definition that we found useful, and we talk about knowledge graph representing some domain of knowledge using active models, which are part of the graph and therefore can be consulted at the runtime. All the information is stored in a graph, which means that it's stored as a network of nodes and links, as opposed to, for example, in a relational database, you have rows and columns. Both data and models or metadata schema represented in the same way part of the graph, and by doing that, it carries semantics together with data and supports various capabilities, including ability to infer new facts, for example. And finally, a very important aspect is that it's based on open standards from top to bottom, data models, queries, etc. Because you're never going to have all the information you may want to have in one place. There's always going to be multiple places, multiple graphs where information can be stored. And there's a movement to open data, for example. So ability to connect these different islands of knowledge together in united knowledge graphs, and doing that seamlessly is very important, and you can't really do it without standards and openness. And finally, the knowledge graph should be able to expand and evolve over time, again, because you discover new information, you want to add to it, your knowledge grows, and ability to easily evolve the graph is very important in our view. So let's give you a little example, kind of like a knowledge graph recipe. You on the left here, you see a small model of information describing organizations, the fact that they have different brands, which are vehicles, and subtype of the vehicle is a car, and each car has a design model and can be manufactured and designed in a certain year. And then you have on the right, you have some data about BMW as a company, has some models. The models have a year. So this is what you have on the left is kind of a blueprint for your graph. What you have on the right is the actual data part of the graph, and they put together, they form together jointly, they form a knowledge graph. So in other words, ontologies plus instance data, you get your knowledge graph. With that introduction, let me now move to property graphs and describe that data model. There's one caveat that I need to make in the beginning, that with like RDF Knowledge Graph, there's standards by the W3C, and all vendors implement those standards. So you could talk about what they are and the representation underneath and say it's the same across. With property graphs, it's not quite the same. There's lots of similarities and lots of common qualities, but there are still some differences in implementation. So that's why I have to make this caveat. What I'm going to talk about in terms of property graphs is the same across majority of the implementation, probably 90+%. Definitely it is true for what I will be describing is true for the most well-known property graph implementation, Neo4j. So in the property graph data model, there are three elements. So there are nodes, which are entities in the graph. There are edges that connect them. There are direct links, they call the relationships. And then there are properties. These are key value pairs that can be hanged on either nodes or edges. So let's take a look at an example and build it up. As an example, I'm gonna use some data from movies and actors and general entertainment domain. So here we have a node. You see the ID of that node is 123, and the IDs get assigned by the system. And of that node, we see some key value pairs, which are the properties: first name, last name, year born. And by this, we understand that this node represents Tom Hanks. And then on the right of the node, we see some blue information, which also in a blue box, which contains labels. It's kind of the same like properties, key value pairs. You have a labeled person, director, actor, but they have special meaning. This is a labeled property graph. So essentially, these are types. Then you have another node up above 125, and that represents post, and that's the movie. You see that from the label. And then finally, there is a connection, an edge between them, and that edge has ID as well, and it has a type. Now this is a little different. Sometimes those types, they're similar to labels on a node. Sometimes they call types. Sometimes, for example, in Microsoft Graph, they are not called types, they call something else. That's one example of the difference. But it gives you basically a nature of the relationship. And you could hang property key value pairs of that edge as well. And here we see that Tom Hanks in this particular movie played the role of Ben Bradley. You see a little legend on the right that helps you figure out the schematics here. And now we'll grow our graph. So we see that we have another person. That person is just an actor as well as a person. And that's Sarah Paulson. And she also acted in that movie, playing another role. And now we could talk about the fact that Tom has directed something. It's a TV series. It's a League of Their Own. It has a release date. And we could also talk about the fact that the movie The Post was filmed in various locations that happen to be cities, and they've got names and they've got population. So that's a property graph. Let's now take a look at exactly the same data in the RDF knowledge graph and see how it looks like, and this way we could compare and contrast. So essentially, we're starting with the same segment of the graph. Again, we have Tom Hanks, and that's a node at the center. We see the birth date, a given name, and a family name, and we see that he is an actor and a director, and he's acted in a movie, The Post. So one thing to notice right away is that whether it's a relationship between two nodes representing some data resources that have identity, or whether it's something that has a literal value, like key value pairs in the property graph, they store the same way. It's 1956, Tom and Hanks are also nodes in the graph, and they also connected by the edges that represent relationships in the same way as Tom is connected to the movie The Post. Also take a look at identifiers, because that's an important part of how RDF knowledge graphs work. So here you see Wikidata column Q2263, and you may wonder what it is. So the Wikidata is a prefix, and it stands for this namespace from the Wikidata, which hosts a very large knowledge graph about all sorts of information. And then Q2263 is a local part of that name. So essentially, in RDF knowledge graphs, each resource that has an identity, the identity is a URI. And you could decide how this URI is formed, and you could reuse URIs from some other graphs if you decide so, as well as you could mint your own URIs. So in this example, we're actually reusing Wikidata URIs. Then for things like schema movie, which is a type of the post, and for given name, family name, birth date, we're using URIs for something called schema.org. I will talk about it later on. And then we have our own with a prefix EX, stands for example, just as an example here. All right, so now let's, and that's kind of Tom Hanks information from the Wikidata that you could see if you wanted to connect to it. You could actually gather a lot of information about Tom, and you could take advantage of it without having to capture it in your own knowledge graph. So now let's grow the graph. Now we bring in Sarah Paulson, and she also acted in this movie. And we'll bring in the fact that Tom Hanks directed A League of Their Own, and then we keep on going, and we have information about where the post was filmed in, and the population of one of the cities by plane. So it's the same information as you saw before. Let us highlight again the differences. One is in terms of IDs, where in property graphs, they kind of internal to the graph database, and they generated by the graph database and controlled by that. So there is no notion of reusing identifiers for ease of connectivity across a knowledge graph. While with RDF knowledge graphs, we've got IDs are always global, and those namespaces, URIs, is what gives them a global nature. And they meant to be under user control. If the users want to have control, of course, you could also let the system generate them by just giving the namespace, and then the local name can be generated using whatever algorithm you choose. And then another very important difference is in the structure of the graph. So with property graphs, the properties are key value pairs, which are literal values. They stored, and they are fundamentally different from nodes and relationships. So it's another data structure that stores them, yet another data structure that stores types. In case of RDF knowledge graph, you've got pretty canonical structure. Everything is stored as a node, and then with links connecting them, irrespective of what it is. In fact, even in terms of terminology, you'll hear some differences, because when we talk about properties for RDF knowledge graphs, we mean any property that Tom Hanks may have, whether it's the fact that he acted in the post, the fact that he directed League of Their Own, the fact that he was born in 1956. Those are all called properties. And in a property graph, only literal values that are hanging off the nodes or edges are called properties. And the edges themselves, when you talk about edges, you never call them properties, you call them relationships. So these are two differences that you see right away. When I started introducing knowledge graphs, I spent quite a bit of time talking about model, ontology, schema. So let's take a look of how it's realized in RDF knowledge graph. So here I've highlighted some of the nodes in red because they're kind of special. And in my underlying image, they actually highlighted with bolder green patterns, but I thought that some people may have problems distinguishing them. So just as we get started, I highlighted some of them in red to be very clear. So these are special because they represent types of the information. They always pointed to an edge that is called RDF type. Here we're reusing built-in standard RDF namespace that carries some standard properties, classes, etc. So far, this seems to be similar to the labeled property graph because those types are similar to labels. However, in RDF, they are not just labels. We could say additional things about them, and we will. For example, you could say that actor and director are both subclasses of the person. With this, I don't have to say that Tom is a person. It's enough to say that he is an actor, and then we know that the actor is a subclass of the person. Therefore, we know that he is a person. And I'm stopping highlighting now, but that's a similar kind of thing. We could say that movie and TV series are both subclasses of creative work. And by the way, we could explicitly say that these things like TV series, like movie, like person, actor, etc., are classes. So they themselves have a type. Similarly, we're saying that the city is subclass of administrative area, subclass of place. And we could say additional things about those schema elements from very simple, like, for example, we could say that the readable, human readable label for this property, for this example acted in, is acted in. But we could also say much more sophisticated and semantically meaningful things. So here's more example of the schema. Again, all of it is part of the graph. And what we're saying here is that creative work, which is a class, creative works could have a property called released. And that property should be a date. And we cannot have more than one release date. And you could argue with that and say it could be released in different markets in different dates, but that's a decision we made in this particular model. Furthermore, we also say that the date has to be at least 1900 or more. That's what we decided for our particular model in our world, because we reason that TV series and movies are fairly recent kind of introduction. And today, there's actually a growing number of standards-based ontologies and vocabularies that can be reused and increasingly are used across industries. Here, just a few of them. And SNOMED and MESH are in the life sciences domain. FIBA, financial industry business ontologies. In the financial domain, QUDT is about units of measure and quantities and dimensions. And schema.org is a very popular one created by Google jointly with other search engine vendors such as Microsoft, Bing, Yahoo, etc. And that's for extracting structured data from web pages. So it has all sorts of classes that we're actually reusing about the type of things that people may be talking about on the web pages, such as people, places, etc. And that's what we're using here. It's an example of the mesh. That's a medical subject headings from, as I said, healthcare, life sciences kind of domain. So this type of standards-based ontologies are actually key enablers of interoperability and transparent data sharing and expressing meaning of data, which could be understood by different applications from different vendors and different organizations. So this is our third, possibly the largest difference is the fact that semantics are not part of the graph with property graph, but they are definitely part of the graph is RDF Knowledge Graph. So what happens with semantics in property graphs? Because before you load your graph, you do need to decide on what you're going to have in it. So you're going to have to model. And this data model exercises, if you're working with property graph, done on paper or maybe in some kind of a tool where you talk about what kind of entities you're going to have, what kind of relationships they're going to have between them, etc. And then when you decide, you structure data according to it, but the model remains separate from data. To some extent, it gets encoded in the programs that you create, queries, etc., because they follow the model, so they implicitly, through people developing those queries, they have a knowledge of the model. But other than that, it remains separate. It remains separate from data, either filed in a document someplace or embedded in the queries. So I said early on that when I showed the RDF knowledge graph, that it was exactly the same that represented exactly the same information as a property graph that I showed before. But that's not exactly true, and maybe some of you already noticed this. So there is one difference. If you look at the property graph, you see that we've got this annotation on the edges, on the acted in edges, where we have additional properties hanging off those edges, saying that Tom Hanks played the role of Ben Bradley and Sarah Paulson played the role of Tony Bradley in that particular movie. So another difference here is that in the property graph, all the edges are unique. You see both of them are labeled with the same type, acted in, but they actually have different identity. And therefore, we could hang those properties on each of those edges. In case of RDF knowledge graphs, that's not the case. The edges, the relationships themselves have an identity that's being reused. So our ID here acted in, and if we bring it Sarah Paulson, she'll be connected to this movie using the same predicate or edge called acted in. So the link itself does not uniquely represent the three parts or the factors sentence in RDF world. It's also called a triple, which is the source node, the target node, and link connecting them. So that triple is not uniquely represented by the edge, which presents some question as to how do you annotate it. So there's an answer for it in RDF data model. Basically, what you do, you create another node, and you say that it is about this acted in relationship, and more specifically, it is about the relationship that connects Tom Hanks with movie The Post. And then when you have done it, it's called reification in the RDF world. You could then add information to it, such as you could say, well, Tom Hanks, when he acted in this movie, he played the role of Ben Bradley. This type of structure is called RDF statement. So this is the way you do that, and it may sound as being a bit complex, but in reality, it is very flexible. And since you're using tools and technology, anyhow, it doesn't need to be complex at all. With that, let me do a quick demo of this graph information in TopBraid. It's the information that I just showed you in two different data models. So I just have a small amount of data here about Sarah Paulson and Tom Hanks. And you could see the information we have about Sarah, and we could click here. We see that she played the role of Tony Bradley. We could go to Tom and see the kind of information we have about Tom. We could kind of explore more details and see what what we know about the related entities, and keep on working like this. And it's a graph, so it's always interesting to look at it in the kind of a graph type of visual representation. So we could do that as well. Let me make it a little bit larger. So you see that kind of connection between Tom and movies he either pulled or directed, and you could continue working the graph by expanding them, expanding the nodes. So you see that Sarah Paulson has also acted in this movie, and if you want to know more about New York City, you could decide to expand its type. It's a city. Here we're moving into schema now, so because there are types, and we could see what else we could know about the city. It's subclass of something, administrative area, and we could keep going on like that and seamlessly going from data to our schema type information. I want to point out something else. So let me actually refresh here and create this annotation about who Tom played in that movie. So there is another difference with property graphs that I'm going to talk about a little bit later, is the fact that there is standard serialization of the information in our RDF graph. So you could export this text serialization, and any technology, any product that supports RDF will be able to import it. And that's an example of this serialization. We could look at prefixes. And the reason I'm bringing this up is I want to point two things. I mean, this is how annotation is stored in a short format. In a longer format, there would be RDF statement and so on. But this is a terse turtle format. And then I want you to take a look at it and see what kind of data we have. We have types, we have birth date, family date, given name, absentee, and directed. We've got the label. And now let's take a look at the form. And in the form, we actually have a full name. And the full name is not in the data at all, but we are still seeing it. So that's a simple example of how the active models can be used in the knowledge graph to generate additional data. It's a very simple example, and the reason this works is because we also have a number of rules stored directly in a graph that infer additional values. So these are some simple rules, and this is the one that basically takes a person, their given name and a family name, concatenates it, and dynamically produces a full name. So where the full name is now available to application, is queryable as if it was stored in a graph. It could also be stored in a graph by materializing this rule, but or it could be dynamically calculated. So when you change the first name and last name, the calculation happens. So it's a pretty trivial example, but nevertheless demonstrates the capability. So let me switch back to my presentation, and we've talked about this, and the difference of how you annotate information on a node, the fact that the relationship is in the property graph, each of them is unique, and therefore it uniquely identifies the node link, node triple. And in the knowledge graph, there is relationships are reused, but there is a way to annotate those edges as well, as we just seen. So with that, let's talk a little bit about the evolution, because evolution is very important. One of the reasons property graphs have seen, graphs in general are being interesting to people, and they seeing a lot of adoption, is the fact that you could evolve easily, much more easily than, let's say, structures such as relational database. So let's talk about evolution. Here we have a biplanes, and we have a population of the biplanes. And in principle, you can have multiple populations because city population changes over time. The way it's a property, so key-value pair, the way you do this kind of thing in a property graph, you store multiple values as an array. So I'm looking at this, and I want to say, well, the first population is in 2019, the second population is in 2010, or something like that. How can I do that? Well, you cannot hang annotations on the key-value pairs. You could only hang them on edges or nodes. So as is, this cannot be done. You have to change your graph and turn a property into a relationship. And with that, you're going to do something like this. You could also do some other structure where you, hang a year directly on the node or whatever. But that's an example of what you do. You'll create a new node, label them population. You build a relationship. You move the size as a key-value pair here. You move the year here, and so on. So you actually change the graph structure significantly. And what that means is that your data must be modified. It's not just an evolution, it's actually a modification. And since the structures are different, it also means that the query language retrieves those values in a different way. So the value of the relationship is retrieved in a different way than the value of the property. Therefore, if you change the structure, your queries and your program would have to change as well. Now, how would we handle it in the RDF Knowledge Graph? Basically, we've already saw that with Tom Hanks and a role. We're just gonna do exactly the same thing, because we could annotate any edge, and what's connecting these values are through edges. So we could just, do things like this. So we introduce a new node, we annotate it, saying that it's for a given year. With that, my graph has grown, but it has not changed. So if I had some queries or some programs that were retrieving population values, they still work. There is an additional information I could expand to take advantage of additional information, but I haven't broken anything in my evolution. Let's take a look at another example. So we're saying that Tom is playing the role of Ben Bradley, and right now Ben Bradley is a string, because we could hang properties here, and properties are key-value pairs again, so they are literal. Well, I may be interested to capture information about more people, and including information about Ben Bradley as a person and whatever may be known about him. So how do I do that? I can't say anything additional about Ben Bradley, just like I can't say anything additional about person or director or actor, because they're just a string. Again, what I will do, I will create a new node. So I'm removing that annotation from here. I'm creating a new node, and now I'm hanging those values of that node. So again, my graph structure has changed to accommodate that evolution. With RDF, we've had a string here. We could just simply replace it by the identifier, and kind of get information if we want to from another knowledge graph. Wikidata has something about Ben Bradley as well. So the difference in how you evolve, where the evolution of the RDF knowledge graph is is less intrusive. So the changes in the design can often be done with small impact on existing data and queries. Since I'm talking about queries, it's also important to briefly talk about the query languages that we could use. So with Knowledge Graph, there is a standard query language, Sparkle, that's universally supported. And increasingly, more and more vendors support GraphQL because it's been so popular, and it's very commonly used to build programs that take advantage of applications that take advantage of knowledge graphs. Because the models are stored in the graphs themselves, it's fairly easy to do introspection, auto-generate GraphQL schemas, etc. I mean, at least that's what we do in TopBraid Edge. With property graphs, you have probably the most common query language is Cypher. This is again something that was initially created by Neo4j, and many, if not necessarily all, property graph databases support Cypher in some variant. They also often have their own kind of proprietary query languages, building off SQL or modifying it to some extent. Increasingly, again, GraphQL is supported, but it's the introspection would be not impossible, but kind of hard to do in an integrated way, since the knowledge or the models are not stored. You have to handcraft your GraphQL schemas separately, and then if you load them into the tool, and of course they are loaded separately from the graph, then the tool would be able to use it to provide introspection. But that's kind of a manual step, and again, a separate yet another representation of the model that gets created somehow. There is some work in the property graph community to come up with a standard query language. It's in the process, and we'll see what the outcome of it is. So I've showed you serialization before, and we're going to come back to it, and that's important because you will want to interchange data. So that serialization is, again, in this turtle format. There's a number of other formats. They've all been standardized, and here you see how edges are depicted, how nodes, subject and object nodes are depicted, and this is how the reification or annotation of that edge is stored. So standard serialization for export, I've been showing you turtle format. It's very commonly used, but there are some other formats, JSON LD, for example, RDF XML, if XML is of interest. With the property graphs, there are ways to export the data, of course, but there is no standard format to export or no standard format to import. It becomes, implementation specific. In case of Neo4j, they do offer you a way to import RDF into their environment. So if you have a serialization of RDF, it will be imported, but in terms of the model that I was showing, the kind of rich definition of properties, etc., it will not be recognized as a model. It could be possible to load it in a graph, but it would not be recognized as a model for the data in a graph. I've mentioned a few times during this webinar how knowledge graphs can be connected, internal, external, also different knowledge graphs within your organization, because we all have kind of islands of data that we want to connect. And the way it works is that you could have individual graphs. Here we could have knowledge graph 1 that talks about data elements, parts of data sets stored in some kind of a system. Another graph that is more about our technology landscape, the fact that this system runs on some server and in some kind of virtual machine on a cloud service, etc. So two separate graphs but they can be combined together fairly seamless, quite seamlessly, just because the URIs in both places were the same. So you bring them together and all the data merges seamlessly. And now we are talking about a larger graph with subgraphs. So the notion of merging and dividing graphs and handling subgraphs is very strong and well implemented. And here's another graph that talks about location of the data center, and we could build links across graphs as naturally as we could build links within graphs. And when we have information like this, that's what lets us build inferences. I showed a simple one with full name. Here's another one that will infer that this data set is located in this location. And therefore, if we're talking about the kind of data that's stored there, critical data elements, PII data, and this is some kind of an offshore location, we could understand that there's implications to that by going through this chain of connection and combining this different information that's available to us. And this is another key feature of the knowledge graph, is that there's name graph for partitioning, and there's ability to easily merge and graphs, and they could also self-compose, connecting based on those unique identifiers. So with that, I went through probably all major differences. What I'd like to talk about now is why you may want to use knowledge graphs. And there are a number of reasons. I'm going to focus today on this strategic reason, this move to data-centric systems and architecture from application-centric. Before I talk about it, I'd like to ask you a question to better understand where you are in your use of graphs in your organization. Christy, can you? It's a quick poll, yeah.
The poll should be on the screen now. The question is, where are you in the process of working with graphs? Choose all that apply. So everyone will just take a few seconds to respond to where they are in the process. I will share the results once they are in. Another couple of seconds. It looks like most people have responded. Okay, I'm going to go ahead and close the poll and share those results. There you go.
Okay, so we've got more people who know RDF than people who know property graphs. Interesting. Mm-hmm. And those people are interested in transitioning. That's, yeah, I'm going to talk about it in a moment, but let me talk first about data-centric architecture. So what does it mean, actually? This is a move towards having data that is self-describing and therefore can support multiple use cases, multiple applications. It's a smarter data. It's a data that's easier to share because the idea of data sharing is built in from the design up. So you'll see, I'm not going to read all the, this is application centric, this is data centric. You're going to get the slides and you will be able to read that. I want to explain it by example. So why self-describing data is important? Here's an open data example. We've got some information about road safety, vehicles by make and model, and there's a bunch of data. There is some metadata, so there are labels. So you see this, the columns are labeled F1, F2, etc., and maybe then those things are meaningful to someone. They're not particularly meaningful to me. So we don't really know what this data represents. So just having a label is not enough. The data is only good as its metadata. And here's another example. Here we have labels, and they are more meaningful to the human being, to a person. So we understand this is a first name, last name, company, etc. But if you exchange it programmatically through the systems, you really need to have more precise information about semantics of it than just a name that may happen to be well constructed. You may want to know what format it is, whether it's required or not, the min and max values, etc. And all of this is a kind of rich metadata that is necessary in order for, you know, to have meaningful data and to have data-centric architectures. So some key facts about this that I'd like to call your attention to. If metadata is not readily available, then as we just saw, the data can't really be understood. One cannot be certain that they're interpreting it correctly. If you have metadata that is separate from data, not part of your systems, then your applications won't be able to access this metadata and interpret it. It's also likely that whatever you created during design time and documented somehow will not be evolving. So if someone looks at that artifact, it's going to be different from what is in the real system. So in the end, what do? Well, you look at the code, you look at the queries, and you do that kind of forensic exercise in order to understand what is it that you have. And openness is important. We could all come up with different ways of representing metadata, but if it's based on standards, then there's shared understanding and interoperability, reuse, and so on. Let me show you another example, another little demo that kind of demonstrates what we mean by having different knowledge graphs that connect to each other and have different models. And that's, my previous demo I've showed in TopBraid Edge, but I've showed kind of a very neutral entertainment example of any graph building on any model that you could build in TopBraid Edge. TopBraid Edge also comes with some pre-built models and some pre-built special purpose graphs that capture data sources, that capture technical assets such as application systems, servers, that capture enterprise assets such as your forms, reports, your organization's capabilities. And all of that can come together, and it's all model driven. So the models drive the business logic. And this is going to be a fairly quick demo as well. So you see all these different subgraphs that I have here. I'm going to look at the one that has enterprise assets. And my example is here is in the medical domain. So I have some information assets such as forms and reports. So, for example, patient's discharge, patient discharge form. And we could see all sorts of information about it, including form items that are part of it, etc. And it's referenced in different programs, and we could get that information as well. And in fact, we could look at entire lineage of this information asset to see how it's produced. I have that picture here already for you. So we could see that the patient discharge form is produced by these various software programs and modules, and those links can also be drilled down to see more details of how information flows through the enterprise to actually produce from the applications and the specific data that those applications exchange to produce the patient's discharge form. And we could also see what parts of the organization are involved in this process, such as medical and nursing care, etc. So it's another example of the use of knowledge graphs as we do in Edge with respect of capturing data ecosystem and infrastructure around data for organizations. And coming back to my presentation, this is just a little bit about how ontologies drive the actual forms that we saw for Tom Hanks, etc., and for this discharge form. And you could explore it on your own. So we have a number of customers that been moving from property graphs to RDF knowledge graphs because property graphs are mature systems and they're easy to get started with, but they've been running into some limitations. And here you see the list of those limitations, and they're kind of a reverse of those differences that I was pointing out before. Have to do with capture of schema in a graph, have to do with evolvability, have to do with handling support for inference, etc. If you do find yourself in that situation, there are some steps that you could take to transition. And this is a brief overview of those steps. And if you're interested, you could ask us for more details, but we have experience with it. You could get your data out. As I mentioned, quite often RDF serialization can be produced. Maybe it's available from someone like Neo4j. If it's not, you could always code to produce it. Once you get your data out, the standard serializations can be imported. You could use TopBraid Edge to help you generate model from the data. Most likely you will need to iterate somewhat on this model because the model will be influenced by property graphs and what performs well there, what doesn't perform well there. But so you'll probably want to take advantage of some qualities of the knowledge graphs as you transition. And then there are some steps that you could take for migrating application code, etc. So this is a very high-level overview. As I said, you could talk about details if you're interested. In summary, graphs are very popular. There are two main graph data models that we discussed together today. There are some very mature implementation of property graphs. In the past, there was an opinion that RDF knowledge graphs are more researchy, more academic, less mature, but this is not the case, has not been the case for years with tools like TopBraid Edge and others. They're pretty mature and robust systems that have been in production for a very long time and power important applications. And it's possible to move from property graphs to knowledge graphs if you decide to do so. And we've provided some pointers on the approach you may want to take. With that, Christy, do we have time to take a couple of questions?
Yeah, we are close to 12:30 and there are lots of questions, but let's try and squeeze in one or two and we will provide answers to all the questions via email. So if you haven't already, go ahead and submit your question and discussion point in the question box located on the right-hand side control panel because we will be responding to them post-webinar. So let's start with this one, Irene. How do knowledge graphs compare to property graphs in supporting graph analytics? And which property graphs are known to be good for?
Yeah, that's a very good question because indeed a lot of initial applications and current applications for property graphs have been around data graph analytics, things like node centrality and shortest path, etc. There isn't anything inherent in one data model versus another data model that makes those kind of analytics better than others, and they were available and built into Neo4j. They are increasingly built in and available for RDF knowledge graphs implementation. So it's a matter of the system, what a given system supports, and can be done with either graph data model. I want to talk a little bit about something called index-free adjacency in relationship to this question, because again, Neo4j was the first entrant, well-known entrant in the property graph space, and they kind of championed and pioneered this concept of the index-free adjacency. And they even tried to define graph databases and as only those that use index-free adjacency. You could Google it and look at the various articles, like you have various consultants saying that this is the most important thing about graph databases, and this is what determines them, and this is what native graph databases use. Well, not quite true. So in that same link, you could see, for example, you saw ArangaDB as an example. So you could look at ArangaDB, what they think about index-free adjacency. They actually don't think it's such a great thing. It has limitations in terms of how do you deal with dense nodes. It also has some limitations in terms of how do you deal with distributed data. And this index-free adjacency is about storing the physical address about the related node in your node. Yeah. And so if you have distributed data, then, and increasingly we are in a distributed environment, that kind of becomes a difficult concept. But it could be done with either graph data model, and has its limitations. There's also increasingly hybrid strategies. The indexes can be actually quite capable with smart tools such as Tiger Graph, for example. They just a couple of months ago introduced indexes because they ran into limitations by just using this index-free adjacency. So a rich topic probably can't do it, can't really cover it in this short session, but the short answer is that you could do graph analytics over either of those data models for graphs.
Okay, great. Thank you, Irene. Maybe we can try and squeeze in one more question. We've got several people hanging on here. So let's do this question. Since it is said that property graphs can store anything, why can't they store models of the information they contain?
Right. Another good question. Yeah, often the question starts, well, you could do it with this, but I could do it with that as well. But then you could ask, why haven't you done it yet? So in principle, yes, it is possible. You could figure out how to represent models in a property graph. This, if you figure it out, it's going to be your proprietary way of doing that. How exactly do you represent this? The fact that this is a class, it has these relationships, properties, the property values are this and that. How do you actually represent it in a graph? In the world of RDF and knowledge graph, you have standards for that. We have RDFS, OWL, we have sharable, etc., and they all map to the RDF data model, RDF graph data model. Could you potentially do this work for property graphs? Potentially you could. It's not going to be easy, and it has not been done yet, but potentially at some point in the future, maybe someone will do that. I suspect that will require quite a bit of change in the underlying machinery and representations, etc., to really make this meaningful. Not like you're just storing another information, but knowing that you're storing models that are describing the data.
All right, thank you, Irene. We are well over, and several of you have asked already if we are going to be sharing the slides and the recording, and the answer to that is yes. We are going to share the slides as well as the recording, and we will also be providing a link to our white paper on this very topic, property graphs versus knowledge graphs versus property graphs. And you'll have access to all of that in an email, along with answers to the questions that we were not able to get to. So thank you all for hanging in there and for your attention, and we hope you have a great day. Thank you.